So our textbook decides to separate out substitution and elimination into a couple categories. The category we're going to talk about in this particular section is the useful, quote unquote, substitution elimination reactions. So if you remember from OChem 1, you probably didn't see a lot of these reagents because they didn't fit the easy category for your standard SN1 and SN2 mechanisms. So while those give you the idea of the mechanistic styles and what's going on with them, they aren't very useful as reagents. So our chapter 10 really addresses some of those. So what I went through and did was kind of categorized out those sections so you get an idea of what each of those sections is attempting to do to the overall reaction. So our first and primary kind of system is looking at making better leaving groups. So with the halogen, that was a decent leaving group. But if we had, say, an OH, well, that's not a very good leaving group. So how do you make it better? The next part, because it's still kind of focusing on oxygens, is looking at how you make better nucleophiles. So the nucleophile may come in as relatively weak. How can you make it a stronger nucleophile? For instance, if we looked at water, water would drive largely an SN1 reaction because it's polar protic and it's a weak nucleophile. How do you make it better? Okay? And if you make it better, what are some kind of secondary results that can come out of that? And that usually leads us down into the epoxides and or oxetane functional group. This then also addresses nitrogen as a potential connection for our leaving group and what that means both towards substitution and towards elimination. And then the last one we do when looking at making better nucleophiles is while we have oxygen and nitrogen in our halogens, how could we get a carbon to be a good nucleophile? And so that's what these individual sections are attempting to break down and look at. One of the things that you should remember from OChem 1 are the basic components that go into these individual reactions, both SN1, SN2, E1, and E2, so all those pieces. So we get our nucleophiles, base, leaving group, substrate, solvent, heat. You should, by looking at this chart, be able to fill in what you would expect that particular category to need. So if I was going to look at, say, that first box here, and if we get rid of the strong term and we just say we're looking at a nucleophile, what do I want for SN1? Well, SN1, I want a weak nucleophile. For SN2, I want a strong. I already filled some of this in. Note we have Na for not applicable. We don't want a nucleophile for the elimination reactions. So what you should be able to do is where these are kind of blanks is write in that information. What is a key signifier for that particular mechanistic type for that reaction condition? If you need a review for any of those, check the whatever it is, the description of the video down below, and I will provide reviews towards certain topics. So the nucleophile and the base usually comes in, or I think is one video, okay? Substrate, solvent, and then leaving group gets mildly addressed. So there's 4 videos that kind of address what are those factors and what they end up meaning within a little bit of context towards the substitution and elimination mechanisms. How would you go through and use the overall chart that we're looking at right now? Well, that chart is supposed to kind of act as a summary for these things. Let's say you saw a strong nucleophile. Well, then you could put a check mark in the SN2. You saw a primary substrate, so check mark in the SN2, and we could potentially lean towards a questionable check mark in the E2. If we had a strong nucleophile, it's possible it was a strong base. Okay? Solvent, we noticed it's polar aprotic. There's a check mark in the SN2. Heat, none. Okay. So we would have filled in our chart, and if we go through and look at our totals, 0, 3 checks, 0, 2 questionable checks. If we were to look at those conditions, we would think that if predicting the product that we're probably going to do a substitution and it's probably going to follow SN2 dynamics. That's the point of this kind of chart. It's to give you all those kind of bullet points that allow you to make conclusions about what kind of reaction you're going to run. So it is a useful kind of chart to have in mind and manipulate, both empty for filling in whatever random thing you've got, and also filled in with the little details. I believe our tutoring center has a chart filled in. I've been a little wishy-washy about making that public just because the most useful study tools you can get are the ones you create. So if you aren't creating it, it's a little questionable, which is why I don't fill it in for you. I get you started so that you can start to find that information to back them. Okay. After that, let's go ahead and take a look at oxygen. And if we just singly bond an oxygen to a carbon structure, so we're looking at a generic carbon structure here, that oxygen on our structure is really synthetically useful, right? And it's useful because we've got lone pairs on that oxygen, which in this case, of course, I implied because that was a stupid thing to do. But if we showed those lone pairs, we now have a source of electrons. Okay? That source of electrons means we have a nucleophile or a base. Okay, so that's really cool. Due to those lone pairs, I now have an idea of the potential reactivity. If it was a nucleophile, this could push substitution reactions. If it was acting as a base, it could push elimination reactions. So putting an oxygen in a structure or finding an oxygen in a structure could be really synthetically useful for allowing me to build things outwards. It is also a relatively electronegative element. And because it is electronegative, it's going to withdraw electron density towards it. Okay? So that means this hydrogen starts to come in as a positive, which means if I put this oxygen on here, I now have the potential to have it act as an acid. That's potentially useful. Right? That carbon is potentially positive, right? Or starts to build some positive charge, which means it could act as an electrophile. So this is really neat. If we're looking at this as an actual functional group, this as an alcohol has all of the core kind of elements for reactivity: nucleophile, base, acid, and electrophile. That's really cool. But for those exact same reasons that it has access to all of that chemistry, it's also really bad. Because if I want it to act as a nucleophile, I have to make sure that whatever I'm reacting it with won't bring in one of those other categories of reactivity, because those other categories could react with the other points within the alcohol. So we have to be a little bit careful about looking at this reagent to make sure, or the structure, to make sure that we don't get sidetracked down the wrong path by accident. Right? And so for that reason, if we're going to try and push something like a substitution or an elimination reaction, really what we're trying to say is for those particular reaction types, I'm asking for that group to act as a leaving group. Right? So I really only want this positive aspect appearing. Right? Well, how can I nullify the lone pair electrons on the oxygen and at the same time nullify that positive hydrogen? Right? So I have to think about chemistries that would allow me to manipulate that. Right? One of the easiest things to do would be to go through and add an acid. Because if we add an acid, particularly a strong acid, that's going to nullify the acidity of the alcohol, because the strong acid is more acidic than the alcohol, so I don't have to worry about it anymore. Right? The next part is, because it is acidic, that's going to take the lone pair electrons on that oxygen, and that's going to occupy them with a bond to hydrogen. At the same time, in making that bond, that makes the oxygen positive, which nullifies the other lone pair from reactivity. So by adding a strong acid, I can nullify 3/4 of the reactivity of this structure, so that really the only thing that matters is that I have an electrophilic carbon. Right? And that's going to really kind of drive the chemistry of this. So the next part's going to come in, well, what's going to be the other half of your strong acid? Right? So that's where we see our chlorides, iodides and bromides. So really what we're suggesting is we're going to push a substitution reaction. And so these are all cases of substitution. And you might ask, why would we go there? Well, maybe I don't want all of that reactivity of the alcohol functional group, so I'm going to convert it to a halide. That limits some of that chemistry. Okay, so it's changing the functionality so I don't have to worry about other reactions. So that's kind of cool. What happens if we switch to a different strong acid, H2SO4? Well, H2SO4 is just as strong an acid as those mineral acids. Well, I think they're all technically mineral acids, but the big difference here is that we're looking at sulfate -2 versus the halogens, which I'll just say X minus. Right? So if we think about reactivity behind those, the halogens turned out to act as really good nucleophiles. Sulfate being negatively charged, we might think, well, yes, it is, but again, it isn't because of resonance stabilization. So sulfate's kind of, if you think back to how I've discussed chemistry in OChem 1, sulfate kind of breaks the mold of our pattern of 5 things that we should be evaluating for stability. Those 5 things would be, that would be an opportunity for a question. We start with charge, size, electronegativity, resonance, and induction. We're using resonance as an argument, which is the 4th one through that list. We would assume a relatively low priority. But there's so much resonance available within sulfate that that one kind of counteracts the upper echelons, if you will, of that ranking system. Okay, so sulfate won't act as a nucleophile. So if we add dilute sulfuric acid, what happens? Well, some of our starting material converts to that really good leaving group, and some does not. Okay, why does that become important? Well, if some does not, what do we still have access to? We still have access to that nucleophilic oxygen, which is why we end up doing a substitution, but this substitution ends up doing forming a symmetrical ether. If we up the concentration of the sulfuric acid, now what we're saying is we have none of that nucleophilic structure left over. How could we stabilize it? We have to stabilize internally by doing an elimination. Okay? So what we're trying to do is think about the reactivity of those intermediates and what those pieces are. Okay? So in our next slides here, what we're going to try and do is address some of that reactivity in a little bit more detail. Let's look first at our activation with our strong acids. So our strong acid, if we were to look at a reaction, we need to think about these. Again, because I'm pretty sure we've already addressed it, when we look at these 2 reagents, we need to be thinking about them not based off of functional group, but based off of what's the most active chemistry, what's the most reactive thing there. And in that case, the most reactive thing there is actually the mineral acid. Right? That's our strong acid. Right? So that should be my focus for driving the chemistry. Because it is a strong acid, I'm really looking at H plus and A minus. H plus is the most reactive thing in this solution. I need to neutralize that first. I'll do that by taking the lone pair electrons, because I need electrons to stabilize that positive, and go through and stabilize it. Don't stress about the secondary atoms on this because they aren't a big deal. They're just kind of floating. We now have a great leaving group. Right? Deciding where we go from there could then come down to, well, does it leave on its own? Or is it forced off? Right? That's a split in the mechanism here. And deciding what that split is going to do is a bit tricky. Right? And that's largely going to depend on what's going on with that A minus. Right? Most of the time, because we're looking at a very protic environment, we're looking at it being it leaving on its own. There are certain circumstances, primary alcohols tend to react a little bit more in the SN2 type. So with this system, we do get kind of a blend of both mechanisms, which kind of sucks. It just does. Okay, so we just kind of have to be cognizant of that and think about it. Okay, if we look at it as A minus as a potential nucleophile, it can potentially come in kind of an SN2 type system, where A- clearly came in and attacked at the same time as the leaving group left because we have one step. Or we could look at it in an SN1 type fashion where the leaving group just leaves on its own and we form the carbocation. So it's thinking about each of those mechanistic styles. Okay? The SN2 is now dead and out of the way, so we don't have to worry about that one, but the SN1 now becomes important. Okay? Well, deciding what happens with the SN1 or SN1 type, because really E1 follows that same mechanism, is really going to come down to what A- is. If A- is a nucleophile, that's going to push the nucleophilic mechanism. How do we know which one's nucleophilic? It's in the symbol, N for nucleophile. So if our A- substrate or reagent is a nucleophile, we're going to expect that mechanism. If it's not a nucleophile, that's where we run into that sulfate issue and we could potentially get some weird gray areas. But for the most part, that's where we would shift off and run the elimination. Right? We do have to remember dilute acid versus concentrated acid and what those things mean to the presence of these individual reagents, okay, or reactive species as we move through it. Okay? The primary mechanism for these reactions is unimolecular, okay, or the one type. So that SN2 type branch that we looked at up here is rare. Oh, if I can spell rare right, is exceptionally rare. Okay? It can happen, it does happen when we're looking at primary alcohols, but it's much, much slower because of all the kind of dynamics of the solvent stabilizing the nucleophile and everything else. Right? So that reaction runs fairly slowly when we're looking at that SN2 pathway. Right? One of the things that you might have noted earlier on is that when we looked at those mineral acids, HCl, HBr, and HI, HBr were just given as one-off reagents. The HCl was given with zinc chloride. Right? Why are we adding something else to this? And if we looked at the overall reaction or remembered that overall reaction, zinc chloride didn't show up as in the reaction structures or the product structures. So what's going on with it? Okay. Well, chloride isn't as good of a nucleophile as the bromide or the iodide. Why is that? Cool. So because of that, actually I just realized I may not have told you that, because chloride is smaller, okay, and we're in a protic environment, it has a very strong connection to the solvent, which means it's less nucleophilic. Right? Because it's less nucleophilic, it's not as easy for it to go through and do that subsequent attack, or the nucleophilic attack. So we need something in there to help really drive this reaction and help the reaction along, and that's the point of the zinc chloride. Zinc chloride comes in, and instead of reacting with anything else, reacts with the alcohol. What this does is that this makes an exceptionally good leaving group. Right? So what we're trying to do is, because the chloride isn't as good a nucleophile, we're making the leaving group that much better so we can up the concentration of our electrophile, so that even though the chloride isn't as good, if I generate a high enough concentration of the electrophile, I can get that reaction happening. Okay? And that's the point of this particular reagent. Okay? So our zinc chloride and our HCl. The other reason why I address this one is it is often known as a Lucas reagent. Okay? And that's because, go figure, somebody discovered it and got to attach their name to it. Okay? So why did they attach their name? Just a straight acid substitution doesn't seem like a big deal. Why does adding zinc important? Well, probably because we saw the rate of this reaction was so slow that we're like, it doesn't really happen. And we're noticing differences in nucleophilic character. But then Lucas comes along and adds zinc chloride, and now it works. Okay? Now it works like gangbusters. So cool. because he's now taken a reaction that didn't work and now works, he gets to attach a name to it. That's kind of neat, right? That's our standard kind of protocol. It extra has a name associated with it because this is what is known as a classification test. We can take zinc chloride in HCl and we can add it to an unknown alcohol, right? In the process of that, if we form this leaving group, then we know that was allowed to happen and that the remaining piece was stable, right? Well, for that to be a remaining stable piece, that would very likely need to be a tertiary or secondary carbon structure, which means if I can see the presence of that leaving group, I know that the starting material was a tertiary or secondary structure. It likely wasn't a primary. So as a classification test, I can add zinc chloride in HCl to a small amount of my unknown substance. And if I can prove that the leaving group is present, I know something about that unknown substance. Okay, that's the point of the classification. Okay? What that identifies is that we have a tertiary or a secondary alcohol. How does this work? Turbidity, right? The zinc chloride isn't particularly, or sorry, not the zinc chloride, the alkyl chloride product produced out of this is not particularly soluble in an acidic environment or in that protic environment, which means it starts to cloud up, right? It's not a precipitate in most cases. What it is the formation of an organic layer, right? So it gets a little bit cloudy because there's another phase interrupting with the light. Okay, so the faster this reagent turns turbid, the more likely you're a tertiary versus a primary. If it never goes turbid, it could be primary, or we have no alcohol whatsoever. Okay, so that's kind of the point of that classification. This kind of chemistry, very, very, very fast, right? Which is why we would use it as a classification test, because we're trying to do it quickly, and it gets us information about an unknown structure relatively cheaply. With the costs of spectroscopy going through the floor, it starts to become more valuable to test unknown substances through spectroscopy instead of doing classification tests. So these classification tests, while incredibly cheap, are probably starting to phase out because the cost of the spectroscopic equipment is getting so low that we can get that information more precisely than running a bunch of classification tests. Right? That said, classification tests are historically valuable, and that's one of the reasons why we tend to push them on you, and you have to kind of memorize them. I never did, though, just for the record. So this gets us to our last slide with some kind of examples. So these are all acid activation examples, right? And note, I'm giving you both the reactant and the product, right? So what I want you to do is look at each of these, right? Evaluate what changed. What are those changes? What went on with it? And you should be able to explain what you're seeing, right? Why did that particular result happen? Or in the case of the second one, explain how fast you think that result should happen. Right? So consider your reaction type and your mechanism in presenting these things. Right? And with that, I think I'll pop up with one question here on that very first one. I want you to go through and look at these answer choices and see if you can tell me what happened. And with that, I'll go ahead and walk through the rest of these. If you don't want to look at the answers, that's fine. Okay, so if we go through and consider this, if we look, we moved positions. Okay, we changed locations. Well, the only reason that should have happened is if we moved through a mechanism that would allow a change in positions. Eliminations could be great because that would allow me to take chemistry at 1 carbon and convert it to being at 2 carbons because we have an alkene. So I could be doing an elimination. I could also be doing just a standard substitution because a substitution would allow me to do a shift as long as I could form stable intermediates, which means looking at an SN1 mechanism. Well, we've just said all of these typically follow an SN1 style. So our first step is likely to form that very good leaving group. That leaving group should leave, forming a carbocation. The instant you see a carbocation, you should be, can I rearrange? And indeed, yes, we can. We can do that rearrangement. That rearrangement happens very, very, very fast because we're going from secondary to tertiary. Now the nucleophile can come in, whoops, our bromide in this case can come in and finalize the reaction. So that's why we're seeing this apparent shift in the chemistry. It's because the mechanism is an SN1 and we form a carbocation with the potential to rearrange. Okay, so that's what's happening within that process. If we look at the second one, what's going on with the second one? Well, in this case, what I'm asking is how fast should it occur? Well, if we're going through, we're looking and evaluating our differences. We haven't changed location of the chemistry. We're keeping it at that terminal carbon, which would be a primary carbon, and we're doing a substitution. OH becomes Cl. Right? Well, these were all supposed to be SN1 type mechanisms. A primary should not be SN1. Right? So for this reaction to happen, it's going to be slow because the primary substrate can't stabilize a carbocation very well, which means this reaction should be very, very, very slow because the substrate doesn't support the mechanistic style that's being forced upon it because of the reagents. The next one, right? What's happening here? We've got the OH and we're ending with a pi bond. This one becomes a little bit odd, again, because we're not running a substitution here. We're doing an elimination as we're ending with a pi bond. If we were to predict what happened, H2SO4 concentrated, we might predict something along these lines where we form that carbocation, or sorry, not carbocation, our great leaving group, that could potentially leave, leaving a primary carbocation, which isn't very likely, okay? And yet we're seeing the double bond on the inside. So what's going on with this? This reaction had to somehow shift this chemistry because the chemistry we've got right here is going to be located at these carbons. Had to somehow shift so that we can get the chemistry into that red position so that we could form that double bond. Okay? What happened? You're likely seeing something along these lines. The hydrogen, whoops, that's making a pi bond, is doing effectively a backside attack, an internal backside attack as a rearrangement, forcing the leaving group off. What does that mean? We now form our carbocation here with the carbocation there. Now we're just doing a standard elimination and we'd get our final product. Okay, that's an exceptionally tricky one, probably one I wouldn't test you on, but what we're trying to do here is push the limits, right? Explain what we see, what has to happen, and make sure you use it in a way that makes as much sense as humanly possible. Right? If you've got other ideas on what happened there, feel free to talk to me and see what I think. Right? The last one, note, we're not saying concentrated. It's a bit frustrating. We really should be saying dilute there as added information. Just because we should do it doesn't mean we do, unfortunately. And with those dilute conditions, what ends up happening is that we're going to end up with two species present. We're going to have the starting alcohol, and we'll have this great leaving group. What can then happen is our starting alcohol can act as a nucleophile, eject our leaving group. Admittedly, we'd still have a hydrogen connected to it in case someone wanted to pick that detail out. That is an exceptionally acidic hydrogen. Something's going to pick that up in solution. Okay, that something from solution becomes a bit tricky, so we'll address that right now. I'm saying B with a lone pair, representing it as a base. Note, I'm not saying it's negatively charged because I'm in an acidic environment, so I can't say that. If it's dilute, that B is likely H2O. It could also potentially be other starting alcohol. Both of those species have a lone pair that could pick up that hydrogen. Right? So those are potential things that could pick it up. Why do I not stress about it? Right? Well, one of the sneaky underhanded things we do a lot in OChem is that sometimes that step falls in what is known as the workup. So when you finish a reaction and you added water, say, to the reaction, that's the workup. That doesn't get explicitly shown in a lot of our reactions. Sometimes it does, sometimes it doesn't. So that could very well be part of the workup. We could also explain it through the solvent, water, or the alcohol picking it up, which is why I would argue it's just not worth the trouble to actually specify what it is. And I would either show B with a lone pair if you have to show something. If you don't want to show something, just the single lone pair or the single arrow works great. Okay. And with that, if you got questions, remember you can always send me an email or grab me during office hours to get those questions answered. And with that, we'll go ahead and stop this section also, if I can get my mouse to work.